Okay, so instantaneous power can be represented as instantaneous current times instantaneous voltage, and we provide time dependence for these parameters. So it will be I maximum times sinus omega t minus phi, which is the phase shift between current and voltage, and times delta V maximum times sinus omega t. So we have for instantaneous power I maximum times delta V maximum times sinus omega t times sinus omega t minus phi. So that's time dependence for electric power, which is dissipated over some AC electric circuit. So now we will apply some trigonometric transformation, in particular sinus omega t minus phi, we can represent as follows. Sinus omega t times cosinus phi minus cosinus omega t times sinus phi. So this we keep in mind, and now when we substitute it instead of this product, we get the following expression. It will be I maximum times delta V maximum times sinus square omega t cosinus phi minus I maximum times delta V maximum sinus omega t times cosinus omega t times sinus phi. So we have two terms which will define time dependence of electric power. And now we need to determine the average for one period in order to get some useful parameter, because one thing we deal with instantaneous parameter, but usually we average it over some time interval. So that's why we need to consider first what will be in terms of parameters involved here, what will be a constant parameter and what will actually change. So we need to average over one period. So I maximum, like maximum current, maximum voltage are constant. Frequency omega is constant, but here we just have product with time. So this is definitely parameter we will average over time. Then phi is constant, doesn't change with time. And the same here. So sinus phi constant, and this product we need to average over one period. So we have shown earlier in our discussions that when we average sinus square omega t over one period, it gives us 1/2. So we keep that in mind, and also so this is this part from first term. Here is another part from second term, and this sinus omega t times cosinus omega t can be represented as sinus 2 omega t divided by 2. And if we average this sinus 2 omega t over one period, we eventually will get to 0. So second term will not contribute to the average value for electric power dissipated in AC our circuit when we average it over one time interval. So eventually we will get with P average 1/2 times I maximum times delta V maximum. So, and we need to keep in mind we still have this uh, cosine phi. Cosine phi. So this is the expression for average power dissipated over AC electric circuit. So here this cosine phi is called a power factor and can be represented as the ratio of active resistance to the impedance of AC electric circuit. So now taking this into account, we can proceed further with P average equal um, mm, yeah, probably before we go further, we also quite convenient to express average power in terms of RMS values, so root mean square values. As you remember, it was defined as maximum divided by square root of 2. So now we can write that here it will be IRMS delta V RMS and times cosinus phi. So we don't have this 2 in the denominator when we operate with RMS values. So this is another option how we can represent this average power. So now when we operate with RMS values, let us write IRMS times delta V RMS times cosine phi. Instead of cosine phi, we can substitute this ratio. So we will get IRMS times delta V RMS. And here will be active resistor divided by impedance. So now we rearrange it a little bit. So we move this impedance under VRMS. So it will be IRMS times delta VRMS divided by impedance and multiply by active resistance. So eventually, what this will give us? Delta V RMS divided by impedance. Which current? Exactly. So it will be IRMS. So now we have IRMS square times R. So we see that actually important equation, similar shape for the structure for the equation. We got the same expression for electric power dissipated on active resistor when we have DC current. Nevertheless, we cannot conduct DC current through an AC electric circuit where we have capacitor connected in series because it's kind of open circuit. So it only AC current can flow through. But nevertheless, the average power which is dissipated over AC electric circuit will be dissipated specifically at the active resistor. So active resistor will define how much power will be delivered. In other words, will be delivered from uh, AC power supply to this electric circuit and dissipated. So what does it mean in terms of uh, dissipation energy over inductor and capacitor. So we will lose this energy uh, when we start to create electric and magnetic field uh, in capacitor and inductor respectively. So there will be some energy which is provided from power supply to create this electric and magnetic field and accumulate energy in form of electric and magnetic field. However, it will happen only during charging capacitor or let's say increasing current in the circuit. So that will happen only during half of the period. During the second half of the period, this accumulated energy in form of electric field and magnetic field will come back to power supply. So if we consider ideal capacitor and inductor, means we do not have any energy losses during the accumulation of electric field energy and magnetic field energy, then there is no dissipation of energy over inductor and capacitor, only dissipation of energy happens over active resistor. So no matter what, we um, do not lose energy over inductor and capacitor. However, there is this cosine phi parameter, this power factor, and if we consider, let's say, this equation for average power in terms of RMS values, um, in order to increase the power delivered to the system, to the AC circuit, we want to have this cosine phi equal to unity. So that will be the maximum power which we can, like actually useful power which we can deliver to the AC electric circuit. So that will happen uh, when this angle phi, the phase shift between current voltage, will be zero. So ideally, when the AC electric circuit will be dominated by active resistor. So then there's no phase shift, and we know that there's no phase shift only in that case when AC current flows through an active resistor. If there is a phase shift, then we will get some limited opportunities to deliver energy, um, electric power to AC electric circuit according to this equation, because here we have this power factor. So if we consider our electric power grid, that is a huge AC electric circuit. So we have a lot of consumers, so some huge generator, a lot of course, we have plenty of transformators which allow us to transport energy via long distances. But eventually, that is like some huge distributed AC electric circuit. Taking into account that majority of consumers of electric power possess much higher inductance than capacitance. For instance, you turn on some electric heater, so we have some chromium wire which is heated by current and irradiates some heat in form of infrared radiation to warm up the room or classroom or office. So this configuration possesses much higher inductance because we actually have a solenoid in comparison to capacitance. And there are similar powerful electric energy consumers with much higher internal inductance than capacitance. So we have kind of this balance between reactive, like inductive reactance and capacitive reactance in the natural, like normal electric power distributed system. So in order to keep this angle phi as close as possible to zero, we want to have normal operating conditions close to the option when we compensate inductive reactance with capacitive reactance, because these guys are in opposite phases and they compensate each other. So for that purpose, in order to increase this cosine p coefficient and operate it at conditions close to unity, next to powerful generators at power stations, uh, engineers are connecting intentionally huge capacitors. So in order to compensate lack of capacitive reactance in consumers of electric power, so they kind of locally attach huge capacitors with variable capacitance in order to increase capacitance when more consumers are attached to the electric circuit, electric grid. And that helps to compensate this excessive inductive reactance of consumers and get the cosine p coefficient closer to unity. So now let us talk to related topic, actually, when we want to compensate this inductive and reactive, inductive and capacitive reactance. And what happens when we match them ideally between themselves, so they compensate completely each other. So it's called a resonance of RLC electric circuit. So let us discuss this question. So what will be the current if we are talking about RMS current in AC electric circuit? I RMS will be equal to delta V RMS divided by impedance of electric circuit. So how we define impedance? We remember from previous discussion, delta V RMS will be equal, so it means the absolute value of the magnitude of impedance, that is square root of R square plus XL minus XC square. At some, so we know that these guys XL and XC, they are functions of frequency. So who will recall how XL depends on frequency? What's expression for omega times L? So linearly proportional. And XC, omega C. And so here, with increase of frequency, capacitive reactance decreases. By the way, who remembers what's the reason behind that? Faster. So that allows charge transport to happen easier through the circuit because we can transport more charge per unit time. Okay, so here we have these expressions for frequency dependencies of inductive and reactive capacitances, inductive and capacitive reactance. And at some frequency omega naught, these guys will be equal to each other. So from here, we can express this omega naught frequency, which is called also as resonance frequency. And that will be equal to 1 over square root of the product inductance times capacitance. So now let us consider what will be this maximum RMS current, RMS, will be equal to, again, delta VRMS over impedance. And in this case, if these guys are equal to each other, so this will be equal to 0. So under resonance conditions. So, or at resonance frequency. This will be RMS, VRMS divided by active resistance R. So this is the expression for the maximum current which can flow through AC electric circuit where we have resistor, active resistor, inductor, and capacitor connected in series. So all of them contribute to impedance, but at some special condition, which is called resonance. Inductive and capacitive reactance compensate each other because these guys are in opposite phases. So if we get their magnitudes equal, they compensate each other completely, and current, maximum current through the electric circuit, AC electric circuit, will be totally defined only by active resistor. So we can consider also average power, P average, will be IRMS square times active resistance. So that can be represented as delta VRMS square over Z square times R. And let us write here the expression for impedance. So it will be delta VRMS square over R square plus XL minus XC square times R. So now we know that XL minus XC square, that is omega L minus 1 over omega C square, and that we can represent in the following form: L square over omega square times omega square minus omega naught square in second power. So now we can substitute it here, this expression, instead of XL minus XC, and P average will be given as delta V RMS square times active resistance R times omega square divided by R square times omega square plus L square omega square minus omega naught square. So keep in mind that omega naught is 1 over square root L times C. So now when we have resonance case, so omega is equal to omega naught, this term will be equal to 0, and as a result, P average at resonance will be equal to delta VRMS square divided by R. So, which is another form for representation of electric power dissipated over uh, over active resistance. So we get maximum current, which is flowing through the AC uh, electric circuit when at certain frequency called resonance frequency, the inductive and capacitive reactance are equal to each other in magnitude, and since they are in opposite phases, they compensate each other. Their contribution to opposition of current flow through AC circuit is equal to zero, and it's defined only by active resistance. So now let us consider transformers. So the general construction. For a transformer, we have some ferromagnetic core. We have primary coil. We have secondary coil. So here for primary coil, we have the delta V1, here delta V2. And here we have N1 number of turns per coil, like for this coil, first coil, primary coil, and N2 turns for secondary coil. That will correspond to, can consider like magnetic field flux FB1 and FB2. Considering that all magnetic field lines are confined in the ferromagnetic core of the transformer, we assume that we don't lose any energy. And in this case, FB1 will be equal to FB2, and we can define it as FB. So the magnetic field flux through both primary and secondary coils of a transformer will be the same. So now how we define delta V1, that is nothing else as according to Faraday's law. So we have minus N1 times dFB over dt. So first derivative of magnetic field flux over time. For delta V2, in voltage difference at the terminals of secondary coil will be defined as minus N2 times dFB over dt. So from here, we can write that delta V2 is equal to N2 over N1 times delta V1. So we see the relationship between number of turns for the first and second, like primary and secondary coil, and resultant potential difference at the terminals of the secondary coil if the potential difference at the primary coil is given. So now if N2 is larger than N1, delta V2 obviously will be larger than delta V1. So we are dealing with step up transformer, means we increase the voltage. In the contrary, if N2 is smaller than N1, delta V2 is smaller than delta V1, we have a step down transformer. What is important here assuming that we do not have any losses. And that is not so far from the truth, because modern transformers, their efficiency in transforming electric power from lower to high or higher to low voltage is close to 99%, like the best examples. So considering that we do not lose any power, then the power which is delivered through the primary coil should be equal to the power which is taken away from the transformer through the secondary coil. So we can actually write that I1 times delta V1 should be equal to I2 times delta V2. And now here, usually how it works, we have some load resistor attached here. This is RL. So that's some consumer of electric power attached to the secondary coil. And in this case, it's clear how we determine this current in the secondary coil. So it will be I2 is equal to delta V2 over this load resistor, which is attached to secondary coil, assuming that we neglect with the resistance of the secondary coil itself, a kind of internal resistance of the transformer, secondary coil transformer. So, however, it's not so clear how we define the so-called equivalent resistance of the first primary coil, because we do not have any load resistor connected to it. So it goes directly, let's say, from transformer, and this equivalent resistance will be the function of several parameters. First of all, it will be defined by the load resistor, obviously, because load resistor will define what is the equivalent resistance of the primary coil, but also it will be defined by ratio between number of turns for primary and secondary coils. So we can write that I1 is equal to delta V1 divided by R equivalent. And this R equivalent in its turn can be defined as N1 over N2 in second power times RL. So you see that R equivalent is a function of three parameters: number of turns in primary and secondary coils, and load resistance, which is attached to the secondary coil. So we have few minutes left. Let us consider also rectifier and filter. So when we come to consumer, not always consumer of electric power is designed to use AC electric current. So let's say if we're talking about some laptops or smartphones, we always have power source which converts AC current, what we get from power outlet, into DC current, which actually can charge some batteries and be like operate electric circuits. So how we deal with this? We need to introduce such device as a diode. It can be either vacuum tube diode or a solid state semiconductor diode. So usually, obviously, nowadays we deal with semiconductor solid state diodes because you can make them very compact and they will consume minimum amount of energy. What is the feature of this diode? It has asymmetric conductivity depending on the polarity of bias, which is external bias, which is applied to this device. So if we plot current voltage characteristic, we will see that at reverse bias we have very low current through this semiconductor diode, but at forward bias it increases exponentially. And that feature allows us to rectify, means to cut half of period of AC signal. So that's the electric circuit. We have some AC power supply, which could be considered our power outlet, which we are using every day. Then it goes to secondary coil of a transformer. Then we have, sorry, not secondary, but primary. Then we have secondary coil in order to step down the voltage because again our gadgets are working at lower DC voltage. So it's something like 12 or 5 volts, depends whatever we are using. And in the power outlet we have 220 volts. So we need to step down it, but then we need to rectify it. So we have a diode connected in uh, this electric circuit of the secondary coil and our load resistor, which is actually our device, RL. So in this case, if we look at current as a function of time, so it will look like this. We have half of positive period passing through the diode, half of negative period, which is supposed to be here, is just cut it. It's not allowed to go through the diode. So we have another half of period and so on. Uh, so there are obviously options to improve this circuit because we can use a system of diodes, so-called diode bridge, and it will convert, so it will not cut completely as a half of period, it will just reverse it. So instead, when we are considering some diode bridge, we can end up with such picture. So we don't lose half of the period, it just inverted from negative to positive. However, you still see these oscillations in magnitude, maximum, minimum. So we go to maximum voltage, like or current, whatever current or voltage, and then we go to minimum. So these are so-called pulse DC. And in order to have reliable operation of our devices and complicated electric circuits, we want to have as smooth as possible DC current. So how we reach this? We attach filters in parallel to load resistor, and the easiest option is to connect just a capacitor. So what it gives us, it will create some lagging for current because not all current will go through the load resistors at, at the beginning when current is increased, but partially it will go for charging the capacitor. Then when we, so it will not go up so steep to the maximum. Once it reaches the maximum, and current will start to drop. So the current through the resistor will actually be supported by current of the discharging capacitor because we reduce the current or like AC voltage, but we still have charged capacitor, which will contribute to for some time to drive this current through the circuit. That's why when we have this filter, it actually will be, let's do it like here. It will be something like this. It will not be ideal straight line, like horizontal line, but we will have minimum oscillations in terms of magnitude of current because of using of this capacitive filter connected in parallel to the load resistor. So, summarizing, we considered electric power dissipated in AC electric circuits. We figure out that, first of all, only active resistor defines how much power is dissipated, because reactive, resistance, capacitive, and inductive, they during half of the period they kind of accumulate energy from AC power supply in form of electric and magnetic fields energy, and during the other half of the period they just provide it back to the electric power. So there is this power coefficient cosine phi. Ideally, it should be equal to unity. Then it will allow us to deliver maximum power to the AC electric circuit. We considered also transformers. I've shown how we can determine voltage at the terminals of the secondary coil if we know number of turns, and voltage at the primary coil. Also, we highlighted this feature of the equivalent resistance for primary coil when we know the load resistance of the secondary coil, and of course N1 and N2, which stands for number of turns for primary and secondary coils. And we considered rectifiers, which allow us to go from AC current to DC current, because that is what actually happens quite often when we operate our devices. So first of all, we have transformer, which usually step down transformer, because we go from 220 to much lower voltages, and then we need to use a two-terminal device called diode, which possesses asymmetric conductivity and allows us to rectify current. Either we just cut the negative part of the half of period, or if we use diode bridge, we can just convert negative current during this half of period to positive. And in order to reduce these variations in the magnitude of current, it's already DC current, because it's already in one direction. However, in order to get it as close as possible just to constant value, we are applying these so-called filters, which allow us to significantly reduce the variations in the magnitude of DC current after rectification. And that's already high quality DC current, which can be used to power electric circuits of our devices. Okay, thank you very much for attention. Next time we will start new topic of electromagnetic waves. That will be on Monday. Have a good weekend and see you next week.